Hello, everyone, and welcome to today's webinar. This is How to Engineer Software Part 1, Semantic Models. Thanks for joining us. I hope you're doing well and staying healthy. I'm Jesse Bronson, the Marketing Manager at Construx, and today it's my pleasure to introduce to you Steve Tockey. He's the Principal Consultant here at Construx and the author of Return on Software, as well as his most recent book, How to Engineer Software, which this webinar is based on. Before we start, I wanted to remind you to feel free to submit your questions throughout the presentation. My advice is not to wait until the end, but to ask them throughout. And we should have some time at the end for a brief Q&A. We'll also send you an email once the recording of this webinar is available. And on another note, this is part 1 and part 2 will air on November 10th. So I hope you'll tune in for that one. Steve, thank you for being here. I'll go ahead and turn it over to you.
Thank you, Jesse. Hello, everybody. Welcome. And as Jesse mentioned, this is How to Engineer Software Part 1, Semantic Models. There will be a Part 2 a little bit later, but let's get into, okay, some minor legal stuff. Okay, so my goal is to have you understand how software can and how software should actually be engineered. Mary Shaw, a professor at Carnegie Mellon University, has this quote that's, given our track record, there are fundamental problems with the use of the term software engineer. I agree with that. It is a problem. It is a problem today, but I hope to illustrate A, what the problem is and why it's a problem, and B, offer a solution. So while I believe this is true today, that it is definitely a solvable problem, as I'll show you. Okay. So the roadmap, we're going to start off by talking about software engineering. I mean, bottom line, a lot of people are using the job title software engineer without really understanding what the term actually means to engineers. And so there's my point. If we're going to use the term software engineering, then we should be using the term engineering in the same way that chemical engineers and industrial engineers and aeronautical engineers and civil engineers use the term. I should just mention, by the way, that in many jurisdictions, actually using the job title software engineer would be illegal because it's a legally reserved term where there are legal requirements, much like one cannot call themselves a doctor, one cannot call themselves a lawyer, one cannot call themselves an airline pilot without having met some minimum set of legal requirements. And as I said, in many jurisdictions, there are legal requirements to the use of the term, the job title software engineer. So the question then is, what should the term really mean? And why should we care that that's what the term should really mean? Then we'll go on and talk about the idea of the reason that we write code is to always automate. I'm going to use the term a little bit loosely here, but business. There are some set of policies that the software exists to enforce. There's some set of processes that the software exists to carry out. And that's the job of the software, is to automate those policies and processes. Now, we can then build something that you saw in the title, a semantic model. It's really, literally a blueprint of those policies and processes. Then we can also build a similar blueprint of the technology that we're using to do the automation, the programming language, Java, C#, C++, Python, whatever the programming language technology is, there are semantics of that. And based on this notion of what a semantic model is, in terms of model of the business to be automated, and then knowing that there are semantics to the automation technology, that we are then able to talk about what code really is. So when a programmer really writes a line of code, what is the meaning? What is the philosophy of lines of code? And we'll talk about that. The track record, that variants of the approach that I'm talking about here have actually been used on real projects dating back for 35 years with a consistent record of very positive results that we'll talk about later. So I just want to be sure you understand that this is not some proposal that might work, that this is a tried and true method that has been used rather extensively, and as I said, continuously showing positive results. And hopefully you'll understand as we talk about the advantages why we're getting consistently the positive results. And then, yeah, there's some disadvantages that we should talk about, and then we'll wrap this all up and then we'll move on. Okay, so that's where we're headed. Now, software engineering, what should it mean? Why should we care? Again, the basic idea is that if you want to use the job title software engineer, because you're using the title engineer, and as I said, that the term engineer is actually a legally reserved term in certain jurisdictions, that the definition of software engineering should be consistent with the definition of civil engineering and electrical engineering and chemical engineering and aeronautical engineering and all things like that. So what should it mean? And then again, why should we care? Getting back at the Mary Shaw quote about there being some fundamental problems with us using the term the way we're using it. Okay. There's an organization in the United States. It's called the Accreditation Board of Engineering and Technology. It's ABET for short. And they are the organization that accredits university programs in engineering. And so if you're a university and you're offering, say, a civil engineering degree program, it may or may not be ABET accredited, where if it is ABET accredited, then it carries a lot more weight with employers. It gives you a leg up in meeting the legal requirements of being an actual licensed civil engineer. Okay, so they define engineering as, quote, the profession in which a knowledge of the mathematical and natural sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. Okay, that's a mouthful, but what I've done here was kind of summarized it down into this little equation that says you might look at engineering as scientific theory, a body of scientific theory, together with a body of practice, together with a topic called engineering economy, where the idea is that the scientific theory and the theory of most engineering would be physics. The theory that's underneath aeronautical engineering is physics. The theory that's under civil engineering is mostly physics. The science that's underneath chemical engineering is, of course, chemistry. Okay. But then each of those fields has a body of practice. What's the right way to do things in the real world? Where the point is that the scientific theory combined with the practice allow the true engineer to propose a set of possible, theoretically viable solutions to some real world problem. And then engineering economy is all about return on investment. And so as a consultant buddy of mine says, it's the theory and the practice that sets up possible solutions, and then the economics is what knocks them down. And the last one standing, the one that has the best return on investment, is the one that the engineer would then go implement. And so if you get a degree in civil engineering, or you get a degree in chemical engineering or aeronautical engineering, you're actually required to take a class in engineering economy and learn how to do the economic analysis to see from a set of potential solutions which one has the most favorable return on investment. Okay. And so if I use that again as a basis, then it should follow that software engineering could and should be defined as, quote, the profession in which a knowledge of the mathematical and computing sciences gained by study, experience, and practice is applied with judgment to develop ways to utilize economically computing systems for the benefit of mankind. And so software engineering in equation form should then be computer science plus practice plus engineering economy. Okay, so computer science and discrete math And so what we would normally look at in a computer science degree program, finite automata theory, set theory, measurement theory, all of the discrete math about proofs and all that kind of stuff, where the practice would be things like fundamental design principles and how to get good requirements. What are good requirements elicitation techniques? Things like the solid principles, if you're familiar with them. Okay, and all of those, not everything, not comprehensively, but that's really the focus of that book, How to Engineer Software. It's really trying to capture the computer science, the discrete math, and the practice in a practical way. And today's presentation is going to go into some of that. There's a lot more in that book that we're covering today, but that's part of what we're covering today is part of that book. For engineering economy, that's the topic of my first book, Return on Software. Now, there's already a YouTube video out there titled Software Engineering 101. It was a lunch and learn presentation that was done a couple of months ago. That will be linked in the description part of the video. And so you'll be able to just click on the link and go directly to it. Or you can do a search by title Software Engineering 101. And that will come up. And the point is that that will go into a lot more detail about what engineering economy is all about and why should we care about engineering. So there's a lot more depth on that topic that we don't have time to go through here. I'll just refer you there to get that additional depth. Under the why should we care, again, this is elaborated in a separate video titled Top 5 Challenges in Software Development. Again, you can do a search on that in YouTube, or the link will be in the description. But the bottom line is that 18% of projects fail to deliver any usable software at all. In other words, they spend a lot of time, they spend a lot of money, and all of the code that got written doesn't do anything usable by the people who paid for it. That's 18% of the time. Now, of the projects that do actually successfully deliver software, which would be the other 82% of the projects, on average, those projects are 42% late. So a 10-month project ends up taking 14.2 months on average, 35% over budget. And so a project that was originally estimated, planned to be $1 million project ends up actually costing $1.35 million on average. Now, in spite of being 42% late, in spite of being 35% over budget, the picture is even worse when you look at the scope that was promised to be delivered in the original schedule and budget, that despite running late, despite running over budget, you're still 25% short in terms of what you actually delivered. And there's an abundance of delivered defects. Okay, so I don't have world information. I don't know what the software budget is in the world, but in 2019 in the US, it was $340 billion on the order of. Now, 18% of 340 billion is $61 billion in cancellations alone. But keep in mind, for this back of the envelope discussion here, that those 18% of projects that fail, they're not randomly distributed. We do know that it's the larger projects that tend to fail more often than the smaller projects, where the point then is that 18% of 340 billion is $61 billion, but then that assumes that there's a even distribution of project sizes. But knowing that the 18% of projects that are failing are biased towards larger projects, then what that tells us is that the $61 billion spent on canceled projects alone is an underestimate. Now, if you roll in the over budget, if you roll in the under scope, that adds in another $72 billion, that adds in another $41 billion. And so in the end, the people that were paying the $340 billion with an expectation of getting a certain amount of functionality For the functionality that they got, they had actually expected to only pay about 166 billion instead of the 340 billion that they actually paid. And so there's a sizable gap between what they paid and what they thought they were getting and what they actually got and what they should have paid to get what they actually got. So more detail on this in the top 5 challenges. And that goes into also a much more detail into the top 5 root causes of poor performance. Why is this happening on projects? Now, there's real data that comes from a number of sources. One of them, my running surveys of organizations when I'm doing classes for Construx. Basically, the data shows us that 46% of the time, the number one problem cited by people who complain about problems on software, and these are the people on the projects themselves, 46% of the time they claim that the number one reason that the projects are difficult has something to do with vague, ambiguous, incomplete requirements. Only 5% of the people that talk about software projects problems don't mention anything at all about requirements. So 46% of the time it's the number one problem. A fair amount of the time it's not the number one problem, but only 5% of the time is it not even mentioned as a problem. Now, 39% of the time, inadequate project management, lack of planning, lack of tracking, lack of risk management, lack of change control, all of those kind of things rolled up there. 39% of the time, that's labeled as the number one problem on software projects, and only 4% of the time is it not mentioned as a problem. So again, there's real live data here that tracks back over about 20 years from various sources that supports those. Now, the remaining 3 problems are based just purely on my professional experience, but I'm hoping that with on the order of 43 years of experience in the industry, that this is a pretty educated observation. Okay, uncontrolled design and code complexity, just the complexity in the design, the complexity in the code just grows like weeds in the gardens to the point that nobody really understands how everything fits together. Overdependence on testing. We try and test the quality into the code after the code has been built. But the problem is that it's fairly well recognized that the earlier you make a mistake, the later you find and fix the mistake, the exponentially more it costs to deal with that mistake. And 83% of the defects in software are actually injected pre-code. They're requirements problems, they're design problems. The net effect of this is that I use a term called R%, rework percentage. If you look at the total number of labor hours that get spent in a typical software project, we have data that shows that about 61 of every 100 labor hours that get spent on software projects are fixing problems that were injected earlier, fixing problems that were problems in requirements, fixing problems that were problems in design. And so if you look back at the $340 billion and the 166 that they thought they should pay, in fact, they could almost pay half of that to get the functionality if we had been controlling the rework. Now, self-documenting code is a myth. The problem is very simply, you can look at code, you can figure out what the code does, but is that what the code is intended to do? What does the code do? What is the code intended to do? Any difference between what the code does and what the code is intended to do is what you would probably call a bug. I would call it a defect. But what is it that tells you what the code was intended to do? Because certainly the code can't do that. And the code can't tell you why it looks the way it does. And so issue number 5 here, root cause number 5, self-documented code being a myth, is not so much a development problem, but is very definitely a long-term maintenance problem. And since about 80% of what we spend on software is spent maintaining existing code, not building brand new code from the ground up, that this is actually a very serious problem. Okay, again, go see the top 5 challenges in software development for a much deeper discussion of all of those problems if you want to follow up on that. Okay, now the point here is that we tend to focus in on syntax, the syntax of the programming language. This is drilled into us from when you first start learning how to write code. What is the syntax of a for loop? What is the syntax of an if statement, etc.? But semantics, I'm claiming, is actually more important than syntax, and we don't really spend much time focusing on that. So just to illustrate, the first example 1, the first statement, the sky is blue, that's fine. The second statement is Chinese. The first 2 characters are the Chinese word for sky. The third character is the Chinese word for is. The next character is the Chinese word for blue, and the last 2 characters are for colored. So sky is blue colored. Now, the next one down is Korean. The first 2 symbols there are sky. The third symbol is a marker that marks that noun to be the subject of the sentence. The next 2 symbols are blue. The following symbol is color, and the last 2 symbols are is. So in Korean, it literally translates to sky blue colored is. Example 2, same idea. I give you this book. The first character in Chinese, I. The second one, give. The third character, you. The next 2 characters, this. And the last character, book. I give you this book. In Korean, the first character, I. The second character is the subject marker again. The next 2 characters are you. The next 2 characters are marking that noun to be the indirect object. The next character is book. The next character is a marker that marks that noun to be the direct object. And the last 3 characters are the verb give. And so I as subject, to you as indirect object, book as direct object, give. And so really the idea here is that syntax is about structure. And so the syntax of English and the syntax of Chinese, while they're not identical, they're very similar. In other words, if you understand how to put together a statement in English, that if you do literally a word substitution, you'll be pretty close in terms of this equivalent sentence in Chinese and vice versa. Now, Korean is completely different structure. You'll notice that in Korean, the verb is always at the end of the sentence. If the verb is anywhere other than the end of the sentence, the Koreans will look at you like you need to learn how to speak our language. Okay, so syntax is about structure, semantics is about meaning. Example 1, these are 3 statements that have the same semantic, they have the same meaning. Example 2, they have the same semantic, they have the same meaning. But again, English, Chinese have very similar syntax. Korean, completely different syntax. Japanese has a syntax that's actually similar in many ways to Korean as I understand it. Now, again, why is this important? Because what you call a bug, what I call a defect, is in fact a semantic inconsistency. Again, there is the semantic that the code has. There is the semantic that you want the code to have. That inconsistency between the semantic that it has and the semantic that you want it to have is the defect. Your compiler is a ruthless master of language syntax. You write code that violates one minor issue in the language syntax rule, and the compiler just basically gives up. And so that's what example 3 is all about. It's trying to get across an example of a statement that is syntactically correct. By all of the rules of English syntax, example 3 is correct. Colorless green dream sleep furiously. Syntactically, that is well structured. Now, semantically, obviously, it's rather meaningless. And so again, your compiler is a ruthless master of language syntax, that the semantic of the code, what do you intend the code to do? What does the code actually do? That's your responsibility. And so until we start to pay more attention to the semantics that we're trying to get the code to have and actually getting the code to have the semantics that we want it to have, we're going to have the same problem that we have with bug-ridden, defect-ridden code. And so that's why we're going to be talking about this notion of semantic modeling. And so, as I said, code automates business. And so for any non-trivial software, we can talk about what is the business being automated? What is the semantic that's being automated? And so as a simple example, if banking is the business, then there are a set of policies in banking software. What does it mean to be a bank customer? What does it mean to be a bank account? Can I have a customer without an account? Can I have a customer with many accounts, or can a customer only have one account? Can I have accounts that don't have customers? Can accounts have only one customer? Can accounts have more than one customer? What are the valid states of an account? What are valid balances of an account? Is it okay to the bank for an account to have a balance that's less than zero? Is that acceptable? Is that not acceptable? And so these are as examples in banking software of policies that the code exists to enforce. Process to carry out. For example, what does it mean to open an account? What does it mean to put money into an account? What does it mean to take money out of an account? What does it mean to move money from one account to another, etc.? Those are all processes that have semantic to the bank. And again, the reason that that banking software exists is to, one, enforce that set of policies, and two, carry out that set of processes to automate the business of banking. Okay, now, as I said, I'm using the term business somewhat advisedly, because if we look at very technical code like the TCP/IP stack, there is in fact a business. There are policies and processes that underlie TCP/IP. What does it actually mean to be a TCP port? What does it mean to be a TCP connection? Can I have a port that doesn't have a connection? Can I have a port with many connections? Can I have a connection without a port? Can I have a connection with many ports? What are the valid states of a TCP connection? What are valid IP addresses for an IP datagram? These are all policy questions that any proper implementation of the TCP/IP stack has to comply in terms of its enforcement of those policies that are defined in terms of TCP/IP. What does it mean to hack a segment? What does it mean to do a window probe? What does it mean to fragment and reassemble IP datagrams? These are all processes that the TCP/IP stack carries out. What do you do when time to live on an IP datagram gives to zero? That again is a process. So again, there's abstractly a set of policies and a set of processes that underlie any implementation of TCP/IP. Whether it's implemented in C, C++, C#, it has to manifest this consistent set of policies and this consistent set of processes. Otherwise, it will not behave in a TCP/IP network. The Angry Bird icon is there to remind me, just to mention that again, there's a business to Angry Birds. What does it mean to be a bird? What does it mean to be a pig? What does it mean to launch a bird into a pig? These are all the business, the policies, the processes that underlie a game like Angry Birds. And so all non-trivial software exists to enforce some set of policies, whatever they are, and carry out some set of processes, whatever they are. Which then leads to the observation that, look, if the software developers want to be successful at automating somebody's business, then those developers need to understand that business at least as well as, if not better than, the business experts understand it. Little asterisk there. The little asterisk is there is to say that only to the extent that the business is being automated. Look, if I'm automating bank deposits, bank accounts, then I certainly have to understand the banking policies and processes. If I'm automating TCP/IP, I need to understand TCP/IP policies and processes. I do not need to know how to run an entire bank. But to the extent that I'm automating bank accounts, I have to understand bank accounts as well as the business experts in the bank understand bank accounts. If that's what they want automated, I have to understand that about the policies and the processes. Okay. And so I call this dreaded SMS syndrome or text message syndrome. Basically, a developer is happy happily developing away, writing code. Their phone buzzes with an incoming text message from the pesky user saying, your stupid software just fill in the blank, where fill in the blank would be something like violated some business policy. Your stupid software just allowed us to have a bank account with a negative balance. Your stupid software just allowed us to have an order without a customer. Whatever it is, to which the software developer, in defense of their code that they work so hard on, might say, well, wait a minute, you never told us that little issue about your business, to which the pesky user says, well, guess what? You never asked. Had you asked, I certainly would have told you. But you didn't ask, so I thought you already knew. And so again, the user, their expertise is in their business. They are business domain experts. They live in their business. They work it every day. And so they make an inappropriate assumption, can I say, of assuming that because they are experts in their business, that everybody else is already an expert in their business. And so the point that I'm really trying to make here is that the onus is not on the business to tell the developers, the onus is on the developers to be able to know to ask the right questions. And so part of this process that we're going to talk about of semantic modeling forces the questions to be asked that are typically otherwise not asked and not answered that lead to defects, this dreaded SMS syndrome. Okay, and so much like there are blueprints of airplanes, there are blueprints of electronic devices, there are blueprints of houses. The idea of a semantic model ends up being a blueprint, literally, of business. Okay. And so some of you are probably, maybe most of you are at least familiar with the idea of the language UML, Unified Modeling Language. Now, before I go there, I want to start off by talking about dialects of natural languages, dialects in particular of English. How English is spoken here in the United States is in some ways different, and importantly different than how English is actually spoken in the United Kingdom. So UK English actually has some subtle but important differences from American English. The same can be said for Australian English, et cetera, et cetera. So there are dialects of these of the language English. Okay, but there are also dialects of the language UML, where by far the most common dialect of UML is what I would call UML for design. I am using UML to describe the structure of a software solution to the business's problem. That is design dialect UML. It's very technology centric. Okay, but most people don't realize that buried in UML is actually a requirements dialect, a semantic model dialect. I'm not talking about bits, I'm not talking about bytes, I'm not talking about database tables, I'm talking about business policy, I'm talking about business process. And so the use case diagram would give me a high-level overview of business process. The class diagram would give me a view of the business policies that need to be enforced. The sequence diagrams would give me process at an intermediate level, and state charts would give me process at a detailed level. This is just an overview. This is just an introduction. But essentially, this becomes a blueprinting language that allows me to capture precisely, concisely, a blueprint of the business policies, a blueprint of those business processes. And the processes you're going to see of building the semantic model forces me to ask questions that would not otherwise be asked in a typical project that would lead to defects, the dreaded SMS syndrome that I was just talking about. So here is an example, a quick example, order fulfillment. These are policies. So consider this to be sort of a mini Amazon.com. What does it mean to be a customer? What does it mean to be a book order? Can I have a book order without a customer? Can I have a customer without a book order? Can a customer have many book orders? Can a book order have many customers? And so there are annotations in the diagram that explain exactly that. So if you understand UML, you would be able to see that a book order must be placed by exactly one customer, no more, no less. A customer doesn't have to have any book orders, but a customer could have many book orders. Now, this is just the diagram. This is just the surface level picture. There's a lot more detail underneath this. Each one of the attributes, like the date opened of a book order, we would actually, to have a full semantic model, we would need to talk about constraints on the date opened of a book order, like the date open cannot be in the future. The date open cannot be any earlier than, let's just make this up, January 1st of the year 1990. But if I didn't tell the developer who's going to write the code that the date open can't be any date in the future, nor can it be any date before January 1st of 1990, because that's when we first started selling books on the web, the developer is probably just going to use a built-in date class, which supports dates all the way back to the 1960s and supports dates into 2038 or whatever that is. With the point being is that since the code doesn't enforce that range, then you're leaving the door wide open for that dreaded SMS. Your stupid software just allowed us to add a date opened in the future. Your stupid software just allowed us to add a date opened in 1972. We weren't in business in 1972. Oh, you never told me there were constraints on date open. Well, I'm telling you now. But as I said, the process of building the semantic model says when there is an attribute on a class, we need to specifically ask what the business's constraints. Is there a latest possible date open, a latest legal date open? Yeah, today. Is there an earliest possible date open? Yeah. January 1st of 1990. We've captured that. We've asked, we got the answer, we wrote it down, we communicated to the developer. There's much more detail we could go into here along the same lines, but we just don't have time. Okay, in terms of process, again, this is a state chart. The idea that there are states that an order could be in, and there are events that the order needs to respond to. These are business states. These are business events. And so if I have an open order and I place it, it depends on if that order has print media, physical books, or it's all electronic books. What do we do? Well, it varies. And this will tell us, for example, that you can cancel a placed order, but you cannot cancel a packed order. You cannot cancel a completed order. And so there are guidelines about how I go about building this model that force me to ask questions like, can I cancel a completed order? And the business will say no. Can I cancel a packed order? Well, I'm glad you asked, because the answer is no. Where the developer may have assumed that, sure, why can't you cancel a packed order? And so this, again, gets at the idea of business process. Okay. In terms of a separate part of a system, how to pay for things. Again, payment policies, payment processes, and I hope you're seeing that these are very definitely non-trivial policies and processes, that if I didn't capture these complex policies and these complex processes in some concise, precise way, there's a very high probability that the code that we write to try to automate these policies and processes doesn't automate it correctly. Okay. And so the process of building these semantic models helps me avoid a huge amount of requirements defects. The first three bullets here, unambiguous, precise, concise, they are about the model itself. A semantic model is unambiguous. A semantic model is precise. A semantic model is concise. It's unambiguous. It has a single interpretation that's derived from computer science and discrete math. And in the lower right there, what you're actually seeing is a fragment of the semantic model of semantic modeling. There's a formal definition of semantic modeling that's grounded in things like set theory, in things like relational algebra, in things like finite automata, measurement theory, etc. And so the meaning much like the meaning of a house blueprint is exactly one thing. No two people will look at the house blueprint and think it represents a different house. No two people would look at the same airplane blueprint and think that it represented different airplanes. In principle, what we're getting at here is no two people should be able to look at the same semantic model and interpret it to mean different businesses. Okay, the model is very precise. If you look at the house drawings, and if you tried to translate the house drawings into natural language, Steve's house shall, Steve's house shall, Steve, it would take hundreds or even thousands of pages to capture everything on the drawings and say it purely in English without any pictures. Well, it's the same idea here with semantic models. They're very precise, that you can, in fact, take the content in a semantic model and translate it into English, but it's going to be hundreds, if not thousands of pages where it's a one-page class diagram, for example. The model is very concise, etc. And again, these are characteristics of the semantic model itself. Now, the process for building the model, there are completeness guidelines. There are checklists that you can use to evaluate a model, and the model turns out to be actually simulatable. It turns out to be executable. And so we can actually demonstrate by executing the model what the consequences of the business's decision. Well, if that is your statement of policies and processes, then this is the behavior you're going to get. If this is your statement of policies and processes, notice that you're going to get different behavior. And so we can actually simulate the consequences of, if that's the way you want your business to be, then this is the way the code is going to actually operate it. Are you sure you want it? Okay. But again, my goal here is to force answering a whole bunch of questions that would otherwise not have been asked, not have been answered. The developer would have made assumptions that would clearly, in a large percentage of the time, would end up being wrong assumptions, which means that the code is wrong. The intent of the code is wrong. The code does not do what the business wants it to do. It's that dreaded SMS syndrome just waiting to happen. Okay, but we can also take this notion of a semantic model and not model the semantics of the business. We can model the semantics of the automation technology. So what are the processes of code development? Well, they are things like this, as expressed in this use case diagram. Fine. This is a small fragment of the policies of a particular programming language. In this case, the programming language happens to be Java. This is by far an incomplete semantic model of Java, but the notion is that it is possible to build a precise, concise model of the semantics of the Java programming language, where the semantics of the C# programming language would in fact be different, and the semantics of C++ would be different, and the semantics of Python would be different. But understand what exactly the semantics are. What are the semantics of single inheritance, a la Java? What are the semantics of multiple inheritance, a la C++? Okay. But now the idea is that if we understand semantic models of business, if we understand semantics models of technology, we're ready to start talking about what code actually is. And so to illustrate that, I want to start off with, in the kind of upper left side there, semantic model of the business. Let's just take banking to be the example. So imagine that cloud is a semantic model of banking as a business. Fine. The lower cloud, semantic model of technology, let's just say that that's the semantic model of Java as the implementation technology. Now, when a developer writes a single line of code, public class account, Java developer writes single Java line of code, public class account, open curly brace, close curly brace, I'm going to call that one line of code. That what that line of code is actually doing is that it's taking the business's concept of what it means to be an account, and it's mapping it onto, in the set theory sense, it's mapping it onto Java's concept of what it means to be a class. So take this concept from the business and map it onto that concept in the technology. Let's look at the next line of code, private double balance. Take the business's concept of what it means to be the balance of a bank account and map that onto a private instance variable in Java of type double. Public void deposit, paren, double amount, close paren, open curly brace, close curly brace. Take the business's concept of what it means to put money into an account and map that onto a member function, map that onto a method in Java programming language. Balance plus equals amount. Take the business's concept about what it means to increase the balance when depositing by the amount deposited and map that onto Java's addition operator. And so the whole point here is that code is in fact a mapping. Code should be a mapping that maps the semantic model of business onto the semantic model of the technology, subject to 3 constraints. There must be 3 important properties in that mapping. Property number 1, the mapping needs to be sufficiently complete. And so what I mean here is, if it's part of the semantic model of the business and they want it automated, then it must have been mapped. If you didn't map it, then it could not have been automated. So the mapping is sufficiently complete. Now, preserve business semantic. The best example of that would be balance plus equals amount. We are mapping increasing the balance in the deposit onto Java's addition operator, because the semantic of Java addition is the same as the bank semantic of increasing the balance on the amount. It would be incorrect semantic to say mapping that onto multiplication or subtraction or division or some other mathematical operation, because that other operation does not preserve the bank semantic. Okay. And so the point then here is that, in fact, at least in my experience, at least in my opinion, is that we have now explained the cause of 80% of software defects. 80% of software defects, in my experience, come about because you don't have a complete model of the business, or you don't have a consistent model of the business. You're mapping from incomplete and inconsistent understandings of business semantics. And of course, if somebody's understanding of the business to automate is incomplete or inconsistent, then the code is going to be equally incomplete or inconsistent. And that is about 60% of the defects in my opinion. Now, preserve business semantic, 30% of the time, roughly speaking. 30% of the time, the developer did understand what the semantic was. They just didn't map it the correct way. Satisfy non-functional requirements has to do with precision, scalability, etc. All of those ILITY kind of requirements. That, in my experience, is about 10% of the time. Okay, and so again, I want to emphasize, you call it a bug, I call it a defect. It is a semantic inconsistency. It is an inconsistency brought on because we did not have a complete, consistent, concise understanding of business semantic, and or when we map that onto the automation technology, we did not preserve the semantic correctly. Now, and if you're familiar with the idea of model view controller as an architectural style, then this talks about what happens in model region. But view controller code is actually also mapping. And so the user interface, if this is the policies and processes for how my user interface is supposed to proceed, when the user clicks this button, we expect this. When the user clicks that button, we expect that, et cetera, that the user interface code is, again, implementing these abstract policies and processes of the user interface. So it just turns out that in one case, the code is mapping from a semantic model, and in the other case, it's mapping from a user interface definition. Okay, so the key implication of if you agree that code is in fact a mapping or code needs to be a mapping, then question, how can software developers successfully automate very complex policies and processes without a complete, consistent, clear, concise, precise, and ambiguous and validated semantic model of those policies and processes to be mapping from? And again, this gets back to my experience of 90% of the defects happen because we don't have a complete, we don't have a consistent, we don't have a clear, concise, precise, unambiguous, and not validated understanding of what those policies and processes are. So, of course, there are inconsistencies, of course, there are incompletenesses, and if you don't focus on preserving the semantic, then of course you're going to build in just more inconsistencies. Okay. And so to overview how this works out on real projects, the background is just setting the whole context for the thing that's being built. The semantic model is the policies and the processes. The interface specification is the definition of user interfaces and APIs and ICDs and things like that. The software design specification is what gets us into code, and of course the code being the actual mapping itself. The crosshatchy figures there that are labeled traceability matrices are really just requirements for consistency. Having said that business policy semantic is, then clearly there needs to be design that enforces and code that enforces that policy semantic. Having said that the progression from screen to screen is, as defined in this interface specification, then clearly there needs to be code that enforces that progression. And so these are the pieces that we get delivered in a project that takes this approach. And of course, again, they need to be consistent. And then the monopoly money is to remind me that all of this stuff has to be done economically. And so this is where the engineering comes in terms of the theory and the practice that underlie building these specifications, deriving the code from the specifications, and doing all of this while keeping an eye on economics. What is the way to do this that gives us the maximum return on investment? And I just need to point out that this is perfectly compatible with Agile. You may look at this and say, oh, goodness, waterfall. In fact, you don't need to do all of the semantic model before doing any of the interface spec, doing all of the interface before. You of course don't need to do that. Of course, you can run through the cycle on a user story by user story by user story basis. Let's take story one. How does that impact the semantic model? How does that impact the interface? How does that impact the design? How does it impact the code? Okay, we got that. Now what's the next user story? How does that impact the semantic model? How does that impact, and do this in a highly iterative and agile fashion? It works just fine, and in fact, it works very well. Okay, so the ultimate goal is to be changing the nature of programming from a private puzzle-solving activity into a public mathematics-based activity of translating specifications into programs that can be expected to both run and do the right thing with little or no debugging. I'm not sure who said this, but very much that is the idea. Designing bridges is not a private puzzle-solving activity. Designing airplanes, not a private puzzle-solving activity. It is a public, to the people that are doing the design, mathematics-based activity. And so why should software really be any different? If you want to call it an engineering discipline, then it must be a public mathematics-based activity. Okay. And so the track record, again, the point here is not that, hey, here's an idea, it might work, you might want to try it, that we have over 35 years or on the order of 35 years of doing projects this way. We certainly don't have a lot of time to go into these in much detail, but I'll just tell you that, for example, automated test equipment on the Boeing 767, 777, and 787 lines were all done with semantic models. The 767 engine sim automated test equipment was estimated to take 14 months. It actually took 7 months. And by the way, based on the amount of code that was written, the industry projections were that the customers of that code would find approximately 75 defects, on the order of 75 defects on the code that got delivered. In fact, they reported 3 defects. And so what we're seeing are fractions of the defects that we would normally expect to be delivered actually being encountered by customers. In all of these ATE projects, the users on the factory floor that were using ATE were expecting it to be a lot more defect ridden than it was. They were shocked and amazed by how well the code actually performed in terms of doing what it was supposed to do and not doing things it was not supposed to do. 777 ATE, 30 months, took 15. 787 ATE, again, 30 months, took 15. P8 Poseidon, this is a replacement for the P3 submarine chaser. This is basically coastal anti-submarine defense. There's a long story behind this, but it's essentially moving P3 technology, updating it to current technology, and putting it into a 737 airframe. Now, our project was not the fly the airplane avionics. That was pretty much off the shelf fly a 737 avionics. What we did was the back end of the airplane, all the mission planning, all the execution, all the submarine detection, the identify friend or foe, weapons and stores management, secure communications, mixed technologies, 350 developers, 7 years, about 7 million lines of code. The code was delivered on time, on budget, with very, very few customer complaints in terms of it doesn't do what it's supposed to do. And so here you have a major defense contract that in fact is delivered on time, on budget, and does what the Department of Defense actually wants it to do, which I credit largely to the semantic modeling of the software. There are many other successful projects that we don't have time to go into, but this has been used at Lawrence Livermore Laboratory, Los Alamos National Laboratory. There are other projects at Boeing, KLA, Rockwell Collins, a company called Peopleware, Nordstrom, Schlumberger, a multinational chemical company that prefers to remain nameless, and I've used it on some internal projects that I've been working on in Construx. And so again, this is not some idea that might work. It's been well exercised, it's been honed, it's been tuned over about 35 years. And so the point is it actually works quite well. Now, in terms of advantages, remember, our number one challenge was vague, ambiguous, and incomplete requirements. But the semantic model is intentionally unambiguous, it's intentionally precise, it's intentionally concise, and the completeness guidelines and the checklists and simulation help us minimize incompleteness. We can never guarantee that anything is complete. But by using the guidelines and the checklists and the simulation, we vastly reduce the possibility that the semantic model is incomplete. Issue number 2 about project management. Now, again, semantic modeling doesn't help with project management. You need to do that with project management things. Okay, but skipping over that, problem number 3, unmanaged design and code complexity. That by separating the semantic model of the complexities of the business from the complexities of the technology, then I have this complete separation, and I've abstracted away and decoupled all of the complexity of the business. And so I can have a precise, concise statement from that over here, and all the complexity of the technology, and they're over there. And so again, 7 million lines of code, automating a whole mission system for the P8, that's definitely non-trivial, but it's manageable in terms of semantic models. The overdependence on testing, I'm not trying to test the quality into the code after we've written the code. I have completeness guidelines, checklist simulations that allow me to find most of the requirements, defects, and design guidelines, the design checklist, to review the designs, and we can find the vast majority of the requirements and design defects before we even get to writing the code. And so in fact, when we go back to that 767 engine sim ATE, remember where we expected to deliver on the order of 75 defects that, on a normal project, that amount of code would have had 75 customer encountered defects. When we looked at the review logs, the review of the semantic model, the review of the design, we found the majority of those 70 some odd defects in the reviews, thus cutting them off before they ever got to the code. we find most remaining requirements and design defects sooner. So we can avoid a whole host of defects. The remaining defects we tend to find much sooner. I mentioned that rework percentage. On typical projects, it's about 61, 62%. 61, 62 out of every 100 labor hours on the project is fixing things that were broken earlier. But on model-based projects, we can estimate that the based on experience, not precisely captured data, that I'm willing to bet that large substantial amounts of money, that rework percent on these model-based projects is under 10%, probably in the order of 7.5% is a reasonable estimate. Okay, self-documenting code is a myth. The semantic model and the interface specification are defining the intent of the code. The code exists to automate the semantics in the semantic model and the interface specification. That's the intent of the code. And so I now know what the intent of the code is. And the design specification should in fact explain the mapping and the why that mapping is chosen. And so quite literally, where I've hopefully proven that code cannot actually be self-documenting, quite literally, I'm turning this around and saying that this is self-coding documentation, because the semantics are of the business, and because the interface semantics are, and because this is the chosen mapping, then clearly the code must look this way. And what this does is it forces us to pay a lot more attention to the semantics. Again, your compiler is a ruthless master of language syntax. You need to focus on semantics because the compiler is no help with that. But if we focus on making the semantic model correct, as we focus on making the mapping correct and preserving that, then the code ends up being correct. And these semantic models, in fact, are highly reusable. And they're highly scalable, as you saw in the P8 case. In terms of reuse, in fact, the fundamental semantic model of 767 Engine Sim ATE and 777 ATE and 787 ATE, there was virtually no code reuse across those projects because they were vastly different technologies. But in fact, the semantic model of what it means to test a Boeing airplane, that semantic model was in fact highly reused across those three airplane programs. There's very little difference in the semantics of testing a 767 versus a 777 versus a 787. The technology, very different, but the semantics of the what does it mean to test an airplane are in fact almost identical. Okay, now disadvantages, that's not the way we've always done it. That simply it comes down to we're not used to building software this way, and because we're not used to building software this way, there's a tremendous reluctance to build software this way, even though we have a track record of very effectively, high quality, on time, on budget, etc. Building software this way, people just don't agree that it can work because it's so different than how we've actually done it, but it does work. Okay, so let me go into summary mode here quickly. And again, this is based on this How to Engineer Software book. I just want to give you a sense of the overall book. So there's some intro and foundations. Part 2 is on semantic modeling. So there are many chapters on how do you build class models, how do you build state models, et cetera, et cetera. Part 3 is on how I take the semantic model and I turn it into actual design, turn it into actual code. There are a bunch of other topics. There's some case studies, et cetera, et cetera. So it's a rather extensive book in terms of the practice of engineering software minus the economics that's in the other book. Okay, so we talked about what software engineering should mean. It should be using science, math, and practice to come up with potential software solutions and then choosing the most cost-effective software solution to implement. And this would reduce the number of defects, it would reduce cost, it would reduce schedule, it would give our businesses a much higher return on their software investment than they're getting now. Again, the code exists to automate some business. What are the policies? What are the processes? I can build a semantic model, precise, concise statement, because if I don't understand the semantics of the business to automate, at least as well as the business does, then I'm not going to automate the right business. I can also, again, build the semantic model of the automation technology, and that code is in fact well-formed code is in fact a mapping from elements of the semantic model of the business onto elements of the semantic model of the technology, subject to the three constraints that it's sufficiently complete, it preserves the business semantic, and it satisfies the non-functional requirements. And there's a 35-year track record of using this successfully on projects. These projects are consistently on time or early. They're consistently on budget or under budget. They consistently deliver everything that was said to be deliverable or deliver more, with a tremendous reduction in the number of defects that actually get delivered. And so you see the whole setup here is precisely oriented to solve these 5 problems. We don't solve the problem of project management, that's different, but vague, ambiguous, incomplete requirements, this solves that. The unmanaged complexity, this gives me a way to solve that. I don't have to depend on testing alone. I can review the models, completeness guidelines. Again, we can put the quality in as we're building it. And at the end of the project, I not only understand what the intent of the code is, I should know why the code looks the way it does, giving the ability to maintain the same code base with far smaller investment. And what we tend to see is when you look at for the volume of code produced, the number of developers needed to maintain it after the initial development drops on an order of factor of 4 to a factor of 8. So cheaper to develop, cheaper to build, cheaper to maintain, higher quality. Okay, so key points. Software projects perform poorly, those 5 problems that we talk about, and the semantic modeling allows me to solve 4 of those 5 problems. Semantics are much more important than syntax. What you call a bug, what I call a defect, is in fact simply a semantic inconsistency. We need to be paying attention to semantics. Code automates a business. I have to understand that business at least as well as the business domain experts. I can precisely, concisely specify that semantic, and the process of building the semantic model avoids a whole host of potential defects. I can precisely, concisely specify the technology semantic. Code maps the business semantic onto the technology semantic, and by doing so in a way that satisfies those 3 constraints, I can avoid all the defects that 90% of the defects that we normally see in code. This directly addresses those mainstream root causes. But again, because this is not the way we've always done it, people tend to shuffle it aside without even trying it. Software can be engineered, software should be engineered, and there's a track record of highly successful projects, so that Mary Shaw's statement, given our track record of that there are fundamental problems with the use of the term software engineer, this doesn't have to be true anymore. And so I've shown you, I hope, how software can and should be engineered. If you would like to track down the references on some of the slides, they are here. There are companion websites for the Return on Software book and for the How to Engineer Software book if you would like to follow up on that. And so with that, let me throw it open to questions. So go ahead, Jesse, and let's move off into the questions.
All right, Steve, thanks for that presentation. We have a few minutes for a couple of questions, so I'll go ahead and ask you those. This was the first one we got in, and you've probably covered part of it, but the question is, what do you think about the ISO SWBOC definition of software engineering? How is it different from yours?
I, in fact, was a participant in the ISO SWBOC. I mean, I'm a reviewer of edition 1. I was actually on the change control board of version 2. Let me say that overall, I think it's pretty good. I've got some minor quibbles with it here and there. I think they missed the boat on a couple of things, but generally overall, yes. And I'll even like to say that if you look at the 15 knowledge areas that are in Sweebot guide that one of those knowledge areas is now software engineering economics, and it is there because I put it there. I basically forced them to include that as a chapter as a consequence of the book. And look, if you want to be really doing engineering, you need engineering economy, and that's why it's there. I put it there. So yeah, overall, yes, minor quibbles here and there, but overall, yes.
Great. Here's the next question. Any ideas or numbers on how poor performance in software engineering compares to other engineering disciplines, and if their problems are similar, for example, poor requirements, etc.?
Well, Mary Shaw, again, wrote a paper. I pulled the Mary Shaw quote, given our track record. That was pulled out of a paper, Prospects for an Engineering Discipline of Software, that shows how civil engineering, the oldest engineering discipline on the planet, dating back to building bridges in the Roman times, shows how it evolved from what was really a cottage craft of bridge builders into a formal engineering discipline. She also goes through the idea of chemical engineering and what was the evolution of chemical engineering. And so the point here is that, in fact, when you look at civil engineering, when that started, when you look at chemical engineering, when that started, yes, they had the same kind of requirements problems. Yes, they tried to test the quality into the bridge after the bridge was built. But now today, you don't have that problem. There is a mathematics, there's a theory of bridge building, there's a theory of chemistry. You do things economically, there's a body of practice. And so while today you don't have the problems that we have in software, in these recognized engineering disciplines, you certainly had them, but that's what drove the formality of what are the underlying scientific principles, what is the underlying practice, where's the economics. And so there is the point that by following the same evolution that Mary Shaw lays out in this paper, that we are on an evolutionary path for making software an engineering discipline. And I'm just trying to push it down that path. Everything that you've seen here is just pushing down the exact same path that Mary Shaw points out in her paper.
All right, and this will be the final question for today, Steve. Does any of this approach need to result in publicly auditable code?
It doesn't need to result in that. And so the whole idea of intellectual property law, of certainly, the crown jewels of some company. I'm not about to take the semantic model of 787 and go try and sell it to Airbus. No, certainly that the violation of intellectual property laws, trade secrets, etc. And so when I said public mathematics base, I didn't mean public to everybody. I think that's what the questioner was reacting to. Didn't mean public to everybody, but public outside of the person who was doing the immediate work. It is auditable by other people, but again, within the constraints of intellectual property law. So I'm hoping that that's answering the question.
Great, thanks, Steve, and that's going to end our Q&A session. Thanks for the excellent presentation, and thanks everyone else for sticking around with us until the end here. And I hope you can join us for part 2 of this series on November 10th. Thanks again, Steve.
Thank you, Jesse, and thanks to all the listeners. I hope you got a lot out of this, and hope to see you later.